I'm glad to see you all in next session of Petroleum Engineering course together with Munavvar, Salmanova and cementing, second part of cementing. So Munavvar, thank you very much for your time and joining, and I'm passing the stage to you now as I think we can start.
Yes, good morning, Wagib. Good morning, all. Thank you for joining and thank you participating here and inviting me. So in the last session, I guess we have the same people, the same auditorium, right? Like I have introduced myself. We talked about a lot about this. Just I don't want to repeat this stuff. If we have the same people here, I will just start to my presentation and go through the second part. So in the last session, if someone is new here, in the last session we have covered the primary cementing, and I guess it was last Saturday, primary cementing, and I have promised you that we will have a calculation for primary cementing, and also today I will talk about remedial cementing jobs, plugs. Also, we have squeeze, but I just keep the squeeze for the next session because I thought that the material is too much for this for one session, and I didn't want to overlap here. I want, first of all, one more apologize for yesterday I couldn't join because we had a remedial cementing job on the rig, and I needed to be in contact with the rig for continuously, and that's why I'm sorry we needed to postpone it. Yes, if we are ready, we can start, but I just would like to ask you which section you would start. First with primary cementing calculation or presentation about cementing plug. Just if you can write here in message that which one you would prefer, I will start with that one. If it doesn't matter, I guess someone is writing. Primary cementing calculations, you mean probably. Okay, first one wrote and went. Yeah, let's start with that one. Okay, then I will share my screen, and Wagif, let's check, please. When I write down here, if you see that, okay?
Yeah.
Because I need to switch cameras for this. Okay. Oops. Okay, just I'll take a picture, and probably you can also take a picture from well data, provided data, and from this page. Or you maybe you do a screenshot, because I will share another calculation, hand calculation. That's why I want you to have this both of them available. Okay, let's see if you see my camera and me. Right. Okay. Like, please check if you can see it. Okay, I write 1, 2, 3. Did you see?
Yes.
It's in right order, right?
Yeah, it's not error.
Okay. Yes, we have covered primary cementing, and I have chosen one of the primary cementing jobs, actual jobs that we have cemented, and I just put input data here. Let's go through the, you all took screenshots, right? I'm not sure about this, but okay, wait. So let's go through there. Probably you see my screen. The objective of this job is cementing of the 18.5 by 8 inch casing. So with inner string method. I have already talked about this in the last session. First requirement for the top of cement to be 200 meters above the previous shoe. Okay, we have a previous casing and we want it to be 200 meters above the previous shoe. I have well schematics here, but I don't want to show you beforehand because most of the time they will not provide you schematic, and you need to take it from text and from tables, whatever information, whatever data has been provided for you. Okay, then let's start. We see that what is the requirement. Spacer ahead 150 barrels and spacer behind 15 barrels. And what are the questions? They are asking us, okay, capacity of 5.5 inch drill pipe. So as we are having an inner string method, it means that we have a drill piping case, right? And the size of the drill pipe is already provided, 5.5 inch. Then capacity of annulus between this current casing and okay, we have open hole size here, 23.5 inch. And then we have a capacity annulus between this case, capacity of annulus between this current casing, current string, and 24-inch casing. So here you can see that we have a previous strings I have put here and the current strings. Previous string we have here 32-inch probabilities conductor, 28-inch surface casing, 24-inch intermediate casing, and again 18 5x8 intermediate casing here. Okay, we have drill pipe, inner string method, and now we will draw schematic manually and we will start to calculate. We have all the parameters of the casings here I have provided for you. We have IDs, we have ODs, and sometimes they can provide you wall thickness. When you get a wall thickness, what you do, I will show you how to calculate ID, but here I have already provided it for you. I didn't want it to be too difficult for you from first time. Maybe in the next sections, I will add some more calculations like liner cementing calculation or plug calculation. And at that time, I will make it a little bit difficult for you. But from first lesson, let's have easy one. Okay, capacities, equivalent open diameter, because I have added 60% of annular excess. I will explain how to calculate it. Volume of the slurry, volume of displacement fluid, top of spacer ahead. When you place 150 barrels of spacer, what will be height of the spacer and also length? Let me put it in length. Calculate both of them. Lengths. And top of spacer ahead in meters. Okay, and shoot rack value. Okay, we are going to calculate it one by one, but now I want you to see this screen camera and here. Okay, I want you all to open well data I provided. First one, we can open the previous strings. Okay. We don't need, if it is casings, we don't need to draw both of them. We can draw like 3 of the previous strings. We don't need to draw all of them. We just draw previous casing. So last casing we have is 24-inch casing, right? From here I will draw it. Let's say it is 24-inch casing till surface. I will write down here 24-inch. Okay, this is 24-inch shoe. Okay, what is the 24-inch shoe? We are using always MDs. Okay, so bottom MD, it is starting from top MD, 0 meter to 1258 meter. So I will write down here 1248 meter. Okay. And then I see, okay, what is my current string? My current string starting from surface to 2380 meter. Okay, I will draw here. I guess in our drilling engineering course in the university, they asked us to draw in the exam, as I remember, or we had some assignment tutorials that we were calculating this. And that was the only thing about cementing in university, as I remember. 2380. And size is 18 5x8 inch. Okay, and what we have here, it is inner string method. Okay, for inner string method, we should have a drill pipe, and it is 5.5 inch. Okay, where is the landing collar? So we talked about these plugs and the inner string. We're having the landing collars. We have a shoe, and we have already discussed it. That's why I would just directly draw it. Landing collar is 2360. It should be somewhere here. What is the depth for my drill pipe? Okay, it is just above the drill collar, 2360 meter. I don't want it too big. Okay, let's get it here, this part. It's 5.5 inch drill pipe. Okay, 5 inch. What is our open hole? Open hole is that section which has been drilled and not cemented yet, okay? So open hole will start from previous casing. We don't care about this open hole because it was already cemented, right? It's already cemented. Now we need to cement this section. I haven't seen orange cement, but anyway. So this part, we will be cementing this part, okay? So because we want to isolate open hole, and also we want to isolate some section between the annulus current string and previous string. And also we will have some cement slurry cement here in shoe track. And we can have some under displacement. I guess I haven't put in the requirement, that's why we will not have it in this section. Okay. Now we start to calculate. Let's see what is required. And we draw this sketch and we have everything right now here. Cement slurry will be here, but what we will have at the displacement fluid, let's say we will have a mud for any SG. If we will require to calculate pressures, I guess it is not required in the table today. I will, in the next sections, I will explain you how to calculate that pressures at the end of the job, what will be differential pressure in the annulus, and okay, we will see it in the next sections. I don't need to mention any mud weights, slurry weights this time because I will go for it after I explain you slurry recipes and cement chemistry. Okay, we have spacer and we have mud and we have slurry. Okay, let's put a sign for them. This will be slurry. If I put Chris, it will be spacer. And for mud, I can have something like this. So this part will be slurry, and I don't know where is top of cement yet. What is the top of cement requirement? Should be written there. It will be 200 meters above previous show. So where is previous show? It is 1,248 meters, right? 200 meters above this, it will be 1,048. Let's say here. So we will have a slurry till here, inside previous casing. So these steps will be top of cement. We write it as a TOC, will be 1,048 meter MD. And okay, let's start to calculate the capacities. First one, it is asking about the capacity. Capacity means that how many barrels, how many cubic meters, what is the volume that it can take. It's required to fill that annulus. It is asking about the capacity of 5.5 inch drill pipe. So I have a 5.5 inch drill pipe. Okay, I have a parameters of the 5.5 inch drill pipe, and it is asking capacity, let's say C1 written there, at barrels per feet. I will give you formula for this for field units. If you want to calculate any capacity of any annulus, you need to go with that formula. Let's say capacity is equal, okay, OD squared minus ID squared by 1029.4. Okay, this will give you in barrels per feet. If you are using OD and ID in inch, okay, OD, ID will be in inch. And then you will get it, this capacity at barrels per feet. Later on, when you want to calculate volume, you will use, if it is provided in meters, you will need to get it in the feet, okay? You will convert it to feet and you will multiply it here to get volume. And capacity, let's calculate now. We know that it will be C1, but drill pipe is not an annulus, okay? Drill pipe is not an annulus. It is something like this. It's a cylinder. So inside cylinder, I want to calculate for 1 meter, for 1 feet, how much volume it is required to fill it. What is the capacity? That's why for this one, I don't have OD. I have OD, but I don't have ID. I don't have another casing inside of this. That's why I will eliminate OD here. I will use only ID for drill pipe capacity. Okay, let's see. So I don't need OD. I will use drill pipe ID squared by 1029.4. And what is ID of that 5.5 inch drill pipe? It has given in the table I have provided. So for 5.5, it is 4.67 squared by. Okay, we got this. And when we calculate it, it will be capacity in barrels per feet. Let's calculate it. I haven't get my calculated, but let me calculate it in Excel. 4.2. So it will give me 0.0. So usually when we manually calculate, yes, we got this value from calculating this. This will be first answer. So let's write down this in presentation as a first answer. Okay, 0.021186. We calculated this. So let's go for second one. Second, it is asking capacity between this casing and open hole. But for this one, I will need to explain you what is the annular capacity in open hole with open hole excess or annular excess. So let's go back. I will delete all of this. I hope you take a note. You took a note, or I don't know. It's better if you took a note. Okay, we said that we can calculate the capacity between annulus and open hole. So here I have an annulus between open hole. Let's say open hole is here like this. And its size is 23.5 inch. But they have asked me for annular excess of 60%. So usually we are using previous wells to get this data. So we know that we have previous wells. In some of the wells we have a caliper, and from caliper we can get the average diameter, and we are using it in the new wells if there will not be any caliper. But in reality, in important strings, let's call most important strings like production and just above the production, or if there is any gas zone or water zone above that. Usually client operator companies are having the calipers, and caliper will give you exact diameter in each meter, even the less than a meter, like a half a meter or in 20 centimeters. Okay, but now we are calculating beforehand. We don't have any caliper data. That's why we will use 60% annular excess. For annular excess right now, when we calculate capacity, we will first calculate the capacity, then we will apply annular excess. Let's find capacity between casing and this open hole. So open hole size is 23.5 inch, 23.5 inch minus inner diameter in this open hole. So outer diameter is our open hole, and the inner one is the outer diameter of current casing. Okay, 5 by 8. Are we okay with that one? So open hole diameter minus outer diameter of this casing will give you capacity of this section. Arrows doesn't show. Okay, arrow this section, this one. That's why now we will eliminate from open hole OD of this current casing. So 18.625 by, okay, let's go and calculate this. If you have a calculator around, you can easily calculate and let me know. That would be better. Minus I'm sorry, it is not 23, it is 23.5. Okay. Yes, our next answer is 0.11494. Okay, we go back for 24-inch and this one, but let me talk about annular excess. So now we calculate the annulus capacity for this section, right? Between our, you see, I guess here, between our open hole and the current casing. And now we want to apply annular excess. What we will do, we will calculate the equivalent capacity. How it will be? It will be capacity, let's have an asterisk here, and it will be this capacity, right, by 1.6. It will be 60% higher than this, and I will calculate it here.
Munavvar, I have a question.
Yes,
from
yes.
Salmanova. So why do you use inches and feet instead of meters?
I have used I'm working in a company, we are using field units. That's why I have used this one. But if you want, I can use metric units. I can switch to metric units if it is easier for you. In most of international companies, we are using only field units, and sometimes they provide meters because easier for meter is very common, and for depths they use the meter. But for other stuff, all of this we are using field units, because most of cement units we have everything. We have their acquisition systems are using the barrels, and they are using inch. Inches are very common for string sizes. Here in Azerbaijan, I have seen in Russia they are using metric units, and in Azerbaijan in some of the projects, old projects, they are using millimeter for casing sizes. But in general, very common one is inch is for casing sizes, and barrels for the volumes. That's why. So this is the only reason I'm using. I can use a different conversion factor. This 1029.4 is coming from conversion factor. When you calculate the cylinder, you can do the same for meters. And I guess I don't remember exactly conversion factor, but we can calculate here right now if you want. Okay. It will be calculated from inch. Now we are calculating it from inch to feet, inch squared to feet, and now you can get it from millimeter squared by millimeter, and you will get it in meters by multiplying 1000. Okay, this is the only difference. You can use both of them, whichever is convenient for you. And then now I got this. For my capacitor, let me write down here because in volume calculation we will need this. I don't want to lose it. 0.6. Okay, let's have it here because later on we will need this. And what is the next question? Guys, is it okay for you right now that this calculations is okay for you? And do you have any question till here? It should be easy, I guess. Any question? Please unmute because I don't see message right now. And you can unmute and you can ask.
Yeah, I have yeah. My eye on the message, so if anyone type on on the chat, I will.
Perfect. Thank you. So I just I'm cleaning this board. Okay, then I will continue with the next question. Next question, I guess, is the capacity between this previous casing and this current string. Okay, so previous casing, now I will need to calculate capacity. It will be ID of, like we in general we say OD squares minus ID, like outer one minus inner one.
I'm sorry, Munavvar Hanım. We have a question from Jamal, and he wants to know what about equivalent OH diameter.
So we have this in the next questions, I guess, or it is the okay. So let me just write down this one. Let me calculate this. After this, I will tell you equivalent open hole diameter. Okay. Like it is the next question. I will go to that. Let's continue with this one because I already wrote this, and then we go back to equivalent diameter. Okay, then capacity between 24-inch casing and the 18.5/8 casing. In this section, we will use inner diameter of 24-inch and minus outer diameter of 18.5/8. And what was the inner diameter there? I forgot. Let me check. Okay, from here. Inner diameter of 24-inch casing is 22.75 inch minus this one. So we use 22.75 minus this one by this 2.8. So I got this number.
I have one question.
Yes, please.
How we get the inner diameter of previous casing from 24-inch to 22.5 inch, if I'm not mistaken?
Okay, it is 22.75. It is provided in the spec sheet. Usually provided manufacturer is giving us the fluid capacity, actually we are calculating from the performance data, but easier one, if they haven't given you anything and they give you only wall thickness. Okay, so let's say it is your casing and it is OD and you are required to get ID. So, and this is the, let's say, T thickness. Okay, sorry, you don't see I am writing because, okay, I wrote something here, but you didn't see. So let's say it is casing, right? Just one wall of the casing like this. This is your OD and you need to calculate what is your ID and thickness. Easy calculation, you need to have two of them to calculate one. Either manufacturer should provide you OD or ID, or OD and thickness, or ID and the thickness of the wall thickness. And how you calculate from this circle, you have it, okay, you just have it as a diameter. So your OD minus 2 times of the wall thickness, because you have this part and you have this part, right? 2 times of the wall thickness will give you ID. Okay, like.
Okay, thank you.
Welcome. So one of these three parameters should be provided, but very accurate one you can get in the spec sheets. They provide the performance fluid capacity, and they are giving it the barrels per feet. And now we will do back calculation to get equivalent open hull diameter, and it is very similar to get the capacity inner diameter of the string from performance data. In performance data, they will give you performance capacity because they feel it and they check how much it gets, because sometimes IDs and the drift diameters are completely different stuff. That's why very accurate result you are getting from performance data, and you will need to do back calculation from this in the job. That's what we do actually. That's what every time I do. I get the spec sheets. I calculate. I am doing back calculation. I get ID that is equivalent to performance data, not written one in the manufacturer data, because sometimes it is not very accurate. And now we are calculating equivalent open hull diameter. So we will need. Did I write it somewhere? Yes, I already, yeah, equivalent open hull diameter in inch. So we calculated the capacity between casing and the open hole is 199494 and okay, guys. So we calculated that capacity of the open hole, my annular between open hole and the casing is this one. And when I multiply it by 1.6, I got this value, right? This is the now current annulus capacity with 60% annular excess. Now I need to calculate the equivalent open hole diameter with this one. Okay, what I will do now, I will do back calculation. I have capacity, but I don't have any open hole diameter like this. 9191 is equal equivalent diameter squared minus casing OD like this. So we just do back calculation and it will give us the equivalent open hole diameter. Let's have it here. We will do, let me do it in Excel, it is easier for me. Sorry that I don't know where I put my calculator, I couldn't find it. So what I will do now, I will multiply this one is equal to this multiplied by plus 18.625 inch squared. And then I will need this one under 5. Okay, I got 25. So this ED, I calculated like this. So here where we were, yeah, equivalent diameter, I got some value after calculation. So ED, it will be ED is equal to this one by square root of this plus 18.5 by 8 squared. All are in the square root, sorry, very dirty. So just ED. Right here, you will not see. Okay, this calculation will give us what is ED is equal. This will be our equivalent diameter, and I calculated it is 25.98972. Okay, so we calculated and then we get this value. Now we had 23.5 inch open hole diameter. We applied 60% annular excess, and we got around the 26 inch. Okay, we got a higher open hole diameter, so that is the kind of safety factor, because while drilling you can get some washouts, you can get over gauge hold, and we are using open hole excess or annular excess to cover these washouts, and to consider that we are not pumping less volume, just to keep the capacity full if we have any washout, because this is the probably 23.5 inch open hole. It comes from bead size, and we are drilling with bead, but sometimes you get some washouts. There can be soft formation. In soft formations, when you get a lot of washouts, you are using higher excess. In surface casings, for example, usually we are using 100% excess, sometimes 150% excess, based on the data from offset wells. In offset wells, like once they run caliper and they see, okay, in one of the wells they have got caliper size, mean caliper size is higher than 2 times higher than this bead size, and then in the next wells they use as a tendency. So usually if you have offshore wells, if you have a very expensive wells, each time they run a caliper. But if it is the cheap land ring and they cannot go with caliper every time, that's why usually clients and the operating companies are using the offset data from previous wells. So now our equivalent diameter is 25.98. 25.9872. Okay, now we need to calculate slurry volume in barrels, and to calculate how much slurry we need to, let me take this as picture then photo from here, because
we have a
Yes.
question in
Yes.
chat box. So Salmanova asks, does it mean that the outer diameter extends?
Outer diameter extends? No, this is the open hole diameter. Let me see the question. This is the open hole diameter. It is not extend yet. We are getting bigger open hole diameter in this case. Let me see. Does it mean that the outer diameter extended? Yes, it is increasing. Actually, in the well, it is, you see this one. Sometimes we get a caliper result, like caliper shows something like that. Open hole comes and then it goes, I don't share. Yes, sometimes we see something like this. Let me show you. So let's say this is a formation. here we have a formation, and this is a bit. Yes. This is a bit. You are going to drill, and this bit OD is 23.5 inch. In this case, you assume that this bit will drill a section with open hole diameter of 23.5. But in reality, you get some washouts like this, and then it comes, sometimes it gets narrow and formation collapse or something, like not big collapse, I mean, it's very small collapse. And this one. And then you need to cover with some excess, you need to cover these open holes, because when you pump slurry will only cover the capacity of this bit size, and it will not cover this washouts. We call it washouts. So sometimes you can get very over gauge hole like this. That's right. You see, this is a bit size, but you get this washouts here. Sometimes you get under gauge hole, like it looks like this. In some sections, bit hasn't drilled it to required diameter, so it has drilled. Maybe bit was so bit size, bit was damaged, and the bit didn't drill with the required diameter. In that cases, you get under gauge hole, and in the under gauge hole you are okay, because you will get more slurry on the surface, and if you are ready to sugaring it, if you are ready to environmentally safely to eliminate this from surface, it's okay. If you pump more, that's good. But if you are pumping less slurry, then you will not get your top of cement at required depths. And sometimes top of cement is decided based on the zones, right? Water zone, shallow water zone, shallow or shallow gas zone. And if you are not covering this zone, then you will be in big trouble because of safety in the well. I guess I replied that question, right? I answered this one. Is it clear now? Like open hole diameter is increasing. What we are using is a increased extended, if you mean that one. So we calculated all of this, and now time to calculate slurry volume. And let's draw it one more time just with the capacities. What we need. We need to calculate capacity. We have calculated capacity C1, C2, and C3. And for volume, how we calculate volume? We have already capacity, and let's say we have a capacity between open hole and our current casing. And now I need to calculate, I will calculate volume in stages, because capacity here and here is not the same, right? That's why I will calculate first casing to casing volume. Volume between volume, let's say, but this one is writing better. Say 18 to 5, 24 inch. Okay, I will need to calculate volume between. What I will do, I will have a capacity by height. And let's call it height, depth, length, whatever you want, you can call it. Let's call it length. Usually it's called with the length. I know capacity, it was the C3. And what was my capacity here? Between casing to casing capacity. Casing to casing capacity was this one. One more time. What is L now? What was my top of cement? My top of cement was starting from 1,048 meter. And where is the previous shoe? It is 1,248 meter. So I need difference. So I know it is 200 meter, but if it is different number, you will need to write down and need to calculate. So what I do, sorry, it is in meters. Now we need to convert it to the feet. And what is the conversion between the feet and meter? So 1 feet, it should be right? I have written there. I guess I know this by heart. Yes, I'm right. So now we will convert these meters to feet. Let's convert it. Yeah, you get any question?
Yeah, there is a question from Kamal. So he wrote, Munavvar Hanım, that whole volume is not included. Isn't that whole volume is in?
No, okay. That's
usually
a good
have too much
question.
that whole multiplication. Sure.
Yeah, that's a good question. Let's go for that. I guess you are somewhat aware about these rattles. So usually what we do, each company has own strategy in calculation in techniques, right? And the company I'm working, we are not considering rattle. In the university, when we had when our professor teach this to us, they covered rattle. In university, probably Heriot-Watt University, they are considering rattle, and there is a reason behind why some companies doesn't take it into account, doesn't consider rattle volume, because when you are pumping, you have a mud there. And this mud because when you are cementing, you put your casing shoe and you have a mud getting viscose below, right? You have a drilling fluid get very viscose. And when you are pumping through this casing, it will come to the shoe slurry, and it will not be jetted down to and clean that rattle volume. Probably that rattle will not be cemented, and usually this volume is very small, like you get 2 barrel, 3 barrel. It's not, if it is not very big hole size, right? In lower casing springs, you are getting very low volume, sometimes half a barrel, and you don't count it. And the reason behind why we are not using rattle, because we consider that fluid has get very viscosified, and slurry will not go through that. Slurry will just move around shoe, and it will go up. Okay, it will not go down. Wherever it is easier, it will go in that section, and that section mud is already behind the casing because you were circulating out, and when you circulate out, that mud is already conditioned, and that's why the slurry will tend to go to up, not down. Okay, that's the reason I'm not using rattle here. But if you want, it is very easy to calculate. You just remember we calculated drill pipe capacity. You take the open hole squared by any conversion factor, and you will get the capacity for rattle. For this time, I will not calculate rattle, and I said why. Okay.
Yeah,
I know
thanks for
that
detailed
some companies
explanation.
doesn't agree with this. There are a lot of people, especially old people working in this industry, they don't agree with this one. They say no, rattle volume should be included, but we don't include, and I don't include, because I don't think that the slurry, because all simulations, all tests has been done, a lot of technology shows that it's not going down, it goes through the shoe up. Yep. Okay, any more question? Okay, then let's continue. Let's convert it to the feet. We have a 200 meter length and 200 meter by 48. I will just calculate and write down here. It will be 60. Sorry, I need to divide it, not 0.30, 200 by. So it will be 650. It will be, okay, let's write down like this. I just use this one, okay? Okay, I got this number. I don't know if you are also calculating there. If you are getting different number, please let me know, because I'm using my phone. I couldn't find my calculator. That's why I can make any mistake easily. So guys, we calculated volume for this section, this capacity between casing to casing from top of cement to here for 200 meter. I just converted 200 meter to the feet. It gave me 656 feet, and I had capacity in barrels per feet. Okay, I multiplied it by feet and I got it in barrels. So volume between casing to casing, it is 188. Let me write down it here because in the end we will need to sum it. And then let's calculate the other capacities. So we have already only 2 and the 3 section. One is the shoe track. So I calculated this section. But for this open hole section, now I will use the capacity with excess. Okay, because we multiply that we get a new capacity. So here it will be open hole and 8 and 6 to 5. Okay, let's go. Okay, what was our open hole capacity by? Yes, it was here. Yeah, it was this one. What is that one? Okay, this one. So now we need to calculate again the length. It will start from current shoe, okay, minus previous shoe. And it will give us 2 meter. We will multiply it by this meter and just to convert it to the feet. So it will be, oops. Get my charger. Give me a second, guys, please. Now we are safe. Okay, I got 1,185 barrel. So this will be the second slurry volume we are required. And then there is a last section for shoe track. And I guess I didn't calculate the capacity for shoe track. Let's calculate the capacity first for shoe track. So capacity will be inside diameter of the current casing. What was the inside diameter of current casing? It was here. It is 17.625. So we need just let me calculate capacity for 17.625 squared by Okay, what is our shoe track length? So our landing collar was at, I guess, 260. Okay, so I have only 20 meter. For this 20 meter, I'm just multiplying for volume. I multiply this capacity by 20 meter by conversion factor. So I got here. So shoe track volume will be this one. Okay, so now when I will when I will sum all of these volumes, it will give me total slurry volume required for this job. So this is the slurry volume required, 1,313. As it is a surface casing, we are getting that much volume. And can someone answer my question? Why we are using inner string method here? Last time we talked a lot about inner string method. Why we are using inner string method here? What is the favor of inner string method here? Time for questions.
Inner string is used because the diameter of the casing inside diameter is more. That's why if we use the plug, it can stuck there. Also, we need the higher volumes to pump cement slurry inside the case.
Okay, yes, that is right. Otherwise we have required a lot of displacement volume, and you see, for now we are pumping 1,000 barrel of slurry. That is too much. Okay, guys, that is too much to pump. But now we will use inner string, and we will need all this to displace this much slurry. We will need only inside the capacity of the inside volume of the drill pipe. But otherwise, what we would do, we would need to pump all these volumes up to down to displace this slurry as a displacement volume. That's why we don't want to pump 1,000 barrels of displacement. We will use inner string. Inner string method, it has also some risks, and some client doesn't like to use inner string method, and most of time they don't have exact equipment, exact casing accessorizes for this one, but it is very recommendable in this kind of jobs with high volume. Okay, we calculate slurry volume, and now let's calculate displacement volume. We have already capacity for drill pipe, and we will use the capacity by height. So what is the length for the displacement? It will start from surface till here, landing collar, where we want to keep some slurry below in the shoe. So it will be 2,360 meter, converting to feet, and we had capacity. Where is this capacity? Where is the capacity for the lookup? Yeah, first one, 0.021186. I don't know who answered the question, but thank you for listening carefully. So now, yes, we calculate. So we multiply this by the length. When I'm using notebook, I'm writing very good and very fast, but it is like, since my student times, I haven't written in the board, sorry. I know that I am writing in very dirty style. 0.021186 by 2,360 by 0.3048. It gave me 164 barrels. This is very less volume for this kind of section. But if you would go with inner diameter, we already calculated for chute drag. Did you see only for 20 meter, it gave me, I guess, 18 barrel or something like that, 20 barrel. It gave me 20 barrel for 20 meter. And we can have a rough calculation that the 1 meter for 1 barrel. If we would use the whole string without inner string, we needed to pump 2,360 barrels of displacement volume, and it is a lot. Okay, it is a lot. You wouldn't pump this, like you wouldn't have a slurry for this to pump, because it is very difficult to design this kind of slurry. I guess I am explaining it very slowly because 1 hour already passed. That's why let's go to other questions very fast. Okay, we calculate the displacement volume. I deleted what I have got. I guess it was, it should be on my phone actually. Yes, it is 164 barrels. And length of spacer and shoe track volume. We calculated already shoe track volume. It is 19.8 barrel, and length and top of the spacer. So what is the spacer volume we are pumping? Spacer volume we are pumping is, okay, spacer volume we are pumping is 150 barrel. Now we will need to do back calculation. How we will do? We know that where is the top of the cement, and above that we will have a spacer ahead, right? So we have a capacity for casing to casing. Currently, we know that the top of cement is inside previous casing, so it means that spacer ahead will be inside previous casing. And our previous casing capacity between casing to casings, we have already written in the table. It was casing to casing capacity of 0.1165797.
There's a question in the chat box.
Yes.
So how you determine spacer volume ahead slurry?
How we determine? Okay, this is a very good question, but how we determine, we are using some, there is some assumptions that, okay, you pump usually this much volume when you pump slurry, but the exact calculation we get from simulations. What I do, every company, service companies, they have simulators, they have softwares. In software, it is calculating mud removal efficiency, how much spacer I need to pump, because I'm adding their spacer properties, I'm adding their density, rheology, all the surfactant, solvent, whatever composition, chemical composition I'm adding. And also I'm adding to that software as an input all these mud parameters, what is the yield point of the mud, what is the PY, etc., everything there. And this simulator calculates, I am adding input as, okay, 100 barrel of spacer ahead, and it is simulating, and it takes that, okay, it is not enough to have a good mud displacement, because first this spacer we are pumping to clean the mud cakes from the walls of this open hole and the previous casing, just to clean and to make a better environment for slurry to go and not get contaminated with mud. Because when mud contamination happens with slurry, slurry loses its properties. Now I will not talk about compressive strengths, etc., because we will talk about this in the lab test and cement chemistry. That's why spacer volume ahead is decided based on the mud removal efficiency. And this is the accurate way to do. But sometimes we know by heart, right, this volume you are pumping, let's say in this kind of job, 150 is too low to pump. But also you need to consider that if you are pumping very long column of spacer, you can get a barite settling in spacer. That's why you need to be careful with these parameters when you pump. You need to optimize. You need to optimize it with mud efficiency and the risk of pumping very long column of spacer. Could I explain? Answer is okay? I don't see comments, but if you help me.
It's okay.
Answer? Okay, welcome. Yes, now we were calculating the that spacer volume. It's already provided and 150 barrel. And now we will do back calculation. So we need to get length. Now we have a volume, we have a capacity, but we don't have a length. So volume is 150 and capacity is this one. We need to find length. So length is, I will get it in feet, okay? 150 by 0.165797. I got this as a feet. And let's convert it to the meter. It will give me 275.8 meter. So, okay, you don't see, I guess, my screen, right? Okay, I got 275, okay, let's say roughly 276 meter of spacer. For when I pump the 150, it will give me 276 meter above this slurry. And this 276 plus top of cement will give me top of spacer. Because when top of cement and then you have a top of slurry, so spacer length will define the top of spacer. So 276 plus, where is the top of cement? This one. Let's answer questions on screen. So our question length is 276, let's say, and top is this one. Let's now go to, I guess now I don't need to write anything. I can be back to share screen option. Okay, let me rejoin there. I will close this camera and then I will open the Teams camera. Let's see if you see me. Do you see me right now?
Yeah, it's okay.
Okay, cool. And you see my screen when I share, I guess.
Yes.
It's shared. You see both of us. Yes, okay. We calculated all the stuff here. We calculated shoe track length and the top of spacer, etc. And now we need to see schematics if I have done it right, okay? And now this is the schematics. I guess I took it from our software. I inputted all this data. For us, I don't know if exactly because I just wrote maybe 1 barrel, 2 barrel different here, so you shouldn't get the exact depths. This is the now wheel schematics that we draw, okay? We have an inner string, we have a slurry up to 1034 here, but I used the only 200 meter above the previous shoe, so we use the 1048 meter. So now we did all the calculations, displacement volume, slurry volume required, and the top of spacer. Where is that top of spacer? This one. Oh, sorry, I just made a mistake. I'm sorry. I thought I am calculating top of cement from this. I needed to. Okay, this will not be 1300. I need to eliminate it from this number, top of cement. So it will give me, I'm sorry, guys. I calculated 148 minus 276. So it will be minus. I need to get top of spacer. Why you didn't correct me? So I need to have a top of spacer at the 772 because it will be above that. Okay. So that's all for calculation. Now we can start, I guess, for plug. Please give me all the calculations from here. Any questions from these calculations from here, and then we can continue with different topic. I'm waiting for questions if you have. Guys, if you don't have questions, let's have a 4 minutes break and then we can continue with plug one. We are okay? Let's meet at 12:24 after 4 minutes. Let me take some water, please. Okay, let's meet after 4 minutes, 4 minutes break. I am back, but I guess I said 12:22, right? Let's wait 1 more minute to start. Okay. Okay, let's start then. So first thing today for the lecture part, we will go with plug. So we covered semantic calculations. You all hear me, right? My microphone is open. And do you see my screen? I guess yes, because I have shared it. Yeah, so if everything okay, we continue with that. So for wall semantic calculations part we have done, and now we will go for remedial semantic. First of all, why we need remedial semantic? We talk about the primary semantic. In primary semantic, we had strings, and we were cementing that strings, right? Like we were cementing backside of the annular part of that strings. Now we will talk about remedial strings. Remedial strings is used when you have any complications on the well, like what kind of complications, you get any problem in the well. We will summarize it more in the next slides, but when you need to repair it, you are using the remedial cementing techniques. You got any problem in primary cementing, let's say you cemented that 18 5x8 casing, and you see that you didn't get top of cement at required depths. Now you need to perforate and you need to do remedial cementing job. You will squeeze some cement from perforations to that zone that you want to cement. Or let's say in the open hole you got a problem, and you have a lost circulation, everything, whatever you are pumping is getting lost to the TIF zones. It's called sometimes TIF zones or the lost circulation zones. And in that sections, in that kind of problems, you are using remedial cementing job, or to treat the condition arising after the wellbore has been constructed. So this is for the option I told you. You are cementing the well and you see that you didn't get good cement behind. You run the wire line and you see you don't have a good cement behind casing. Then in these sections, you need to squeeze the important zone, and you are squeezing some additional cement slurry there. So placement of the cement plug and squeeze cementing. These are the two main types of the remedial cementing job. Today we will talk about the placement of the cement plug, different plug types, plug applications that are using. Why we are using the cement plugs? First one, plug, you see like it is a plug, I guess its name explains that what is that. Mainly it is used for the abandonment option. Abandonment requirements for cement plugs is depends on the government regulations. Each government has its own regulation, and each operating company has its own regulation about abandonment, because if you don't put plugs at the if you don't put enough plugs during abandonment, then you can get the water zone, etc., as contaminated. That's why it is very important, and the main, let's say, most common types of the plugs are abandonment plugs, because in each well you should have it. Second one is a directional drilling. I guess in next slides I will talk to more. Let me just move to that slide and talking there. So first, abandonment, directional drilling, site tracking. This plug type is called the Kickoff Plug. Low circulation control situations, we are using plugs. Well control, we are using a very rare one, but in well control it is used. And zonal isolation, conformance, this is also a very common one. So let's go for the next slide and talk about abandonment and directional drilling plugs. I was talking about abandonment. In abandonment plug, I told you that it depends on the regulations. 5, 6, 7 plugs can be put in one well during the abandonment. So you went there and you had a, like, let's go, it was exploration well, you went there and you found out the dry hole, and you cannot just keep and put a cap there, this steel cap only, and you cannot go away, because maybe you get gas or anything from reservoir after a long time, and it will come to the surface. There will be migration to other zones. That's why you should have an abandonment plug. Kickoff plug. Kickoff plug, also abandonment plug is used after production. You produce, and then now you see that you get only water. It is not. It's not commercial okay to commercial okay to produce from this well, and you need to deplete. It is depleted, so you need to abandon this well, and then you are using the same approach. You are putting a lot of plugs there, cement plugs, also some mechanical ones, and a cap. Kickoff plug. Kickoff plug is used when you decide to sidetrack. So sidetrack decision can come from necessity or necessity if you get any problem in the well. Like a job yesterday I did, that's why I'm a little bit tired. So I designed the job because we got BHA stuck on the well, and we couldn't take this BHA out. It was stuck in production zone, and what has been done, the BHA there was exploded. We kept the BHA on the well, and we put a kickoff plug, this kind of plug, and now rig will go through sidetracking and will go to the next borehole, the secondary borehole, new hole. So this is exactly what we did yesterday. So BHA, here in that photo, you said that the bead was stuck and the fishing was done. So, and then you are putting a cement plug on this, and you go for kickoff. There is another option for kickoff plug if the client doesn't want to put in or if it is risky to have a cement plug. Sometimes they are using whipstock. Whipstock, probably you know from drilling, it is this kind of stock, like it is guiding a bead to drill the next hole, not the current one. So whipstock can also be used, and the alternative to whipstock is cement plug. Cement plug for kickoff plug is very difficult because sometimes you cannot get enough strength in the cement to guide you to the next hole, to another hole, not the current one. It depends on the formation strengths or bead type used, because there are a lot of beads, some motor types and others, and each one has its own strengths to kick off. So kickoff plug is another application of plugs used, and it's also very common. And sidetracking, I only mentioned about fishing, but it can be different reason for sidetracking. Like even sometimes before planning the well, 2 boreholes are planned. So they go exploration for 1 borehole, and they say they found dry hole, then they are drilling the sidetrack into the another hole, or like multilateral holes, or etc. There are a lot of options for this, and each sidetracking mostly cement plugs are used. Sometimes first plug is not successful if you don't have a good base for this one. That's why 2 or 3 kickoff plugs sometimes are spotted in the well. The next types are the low circulation control and well control issues. Low circulation is also very common. You know, low circulation, in low circulation case, you get during mud circulations, you are getting all fluid lost to the formation. It can be, but for this one exact low circulation plug, you need to know some formation details. You need to know the type of losses. If it is total losses means then whatever you are pumping, it goes to the formation, and the level in your well is going to be reduced, and well security is not under control at this stage. That's why lost circulation cases are very important to be under control. and you need to know that if you have fracture formation, you need to know that if it is a drilling-induced fracture or it is a chemical-induced fracture. It can be maybe mud is incompatible with your shale and you are getting any fracking in shale. You need to change mud type first before you are spotting a cement. But cement is one of the good solutions for loose circulation, and sometimes when you get very soft formations, it can also provide some strength to the formation after cementing if you squeeze some of cement in. So you see the teeth zone there, seeping into seeping. That's sometimes we call the seep losses. Seep losses means that the losing rate is not that high. It is low. Like you are pumping, let's say, at 5 barrels per minute, and you are getting returns in the surface at 4 barrels per minute, and it means that you are losing at 1 barrel per minute. It's not that much. It's a medium loss, but sometimes you are pumping 5 barrels per minute and you are losing 5 barrels per minute. You continuously need to fill the well from annulus just to keep the level in the well higher to the surface. And yes, cement plug during well control, it is very rare one that when you get an influx using a cement plug, but sometimes it is required because you don't have any option. It just you need to abandon this well because you don't have any option. You cannot cure influx. You are reducing mud weight. It doesn't help. You are using some well control calculations, BOP close, open, etc. But you cannot solve the problem. In that case, as a last option, they are cementing BHA down. Just they keep even the bead, everything in the well, and they are just putting cement over that just to abandon this well, cure that influx, if there is no other option. But usually this is the very, very rare option for you to use in the well control options. The other applications of plug cementing, it is zonal isolation. So for zonal isolation, why they use the cementing? So I put the same photo, I guess, here. Okay. For zonal isolation, first one is the shallow water zones. So when there's a shallow water zone, we are spotting a plug, cement plug, in this zone, and after that, rig is drilling that cement on the well, and they are going to the second zone. So you see there is a caprock zone for B, and let's say zone B water bearing, and they need to put a plug in front of water zone, and after that they will drill. So in this case, this zone, some cement slurry will be squeezed there in the borehole. There will be cement, and it will not allow this water to enter this formation, because when you are drilling the next section, if you will drill it as a once, you drill it once, and then you want to cement all together, all these zones together, then you need to be sure that this water is not going down to this permeable zone, or like from any gas, anything from this permeable zone is not going to the shallow water zone. Okay, just to avoid contamination between formation fluids, you need to isolate these zones, and these are called these plug types are called the zonal isolation plugs. So here I have written to shut off water, to recomplete a zone at a shallower depth, and also to protect a low pressure zone in an open hole before squeezing. So this is the last option, protecting a lower zone in open hole before squeezing. It is usually done like you have this zone, you want to squeeze from this zone, but you have a shallow like low pressure zone there, and you don't want it goes to there, and you don't want to frack that formation when you squeeze. That's why you are using one plug as a preservation, then you are using the second plug for squeezing. It can be a bullheading squeeze, by the way, don't need to be a plug. We will cover it in next session during squeeze job. Any question from plug types, plug applications?
Okay, there's no question in chat box so far. So far.
Okay, then we go back to techniques. So this was plug cementing and plug cementing applications where we are using plugs. And now I will talk about the cement plug placement techniques. So three main cement plug techniques are used, but most of them are as a balance plug method used. In most cases, balance plug method is used. Dump failure, balance plug, and two plug. Let's go one by one. Dump failure is very rare to use, and it is used only you need to pump a few barrels. Like one dump failure is around 3-4 barrels, I guess. Like it depends. There are a lot of types, but sometimes it is 5 barrel, 10 barrel maximum. And you are using a wire line to run this dump failure. It is kind of a tool. You put the cement slurry inside and it goes to down by wire line, and there are some electrical or mechanical opening systems used to open this tool, and this is spotting the plug there. Why we are using dump failure? Because we don't need to put a very big length for this plug, and if you pump this low volume for 400-300 meters through drill pipe, then you will get everything contaminated, and when it reaches to the 5,000 meter, 4,000 meter, you will not get any cement, pure cement slurry portion there. That's why dump failure method is faster, and but it has a risk that this dump failure will be stuck or anything. This kind of risks are available with dump failure. So method is like, let's say you have this tool, you put slurry inside, and you are sending it down. It doesn't have any interaction with upper sections. When it reaches to the point you want to spot a cement plug, you just open it from surface, and the cement slurry is going out and used as a plug, cement plug there. So you can see it from this photo. You have a wire line tool hanging, so it is used to run and hold this dump failure and the cement slurry inside. So slurry, you have a casing and opening mechanism. So as I mentioned, it can be mechanical or electrical one. Mechanical one is using by, I guess, rotating. They rotate these tools a few times, and then there is a specification for each product from each manufacturer. That's why it is different. You need to know exactly which tool you are using. And they are using mechanical one, and this is opening, and then slurry is going to that section. This is for dump failure. I put just one of them from one manufacturer, but there are like different sizes. There are different in the different shape. This one is the slim one. Sometimes you are having something like a bucket one. It has a it is a ball kind of stuff in blue, and upper section is slim. You have a different shape, so it will depend on the manufacturer. So this was dump failure method. We are using it when you need to pump very low volumes. Balance plug placement. This is the very common one for balance plug. What you do, you go down with drill pipe, and you are pumping as in normal jobs, like as an inner stream job. You are pumping all first spacer ahead, then you are pumping slurry, then you are pumping spacer behind. But you need to do a calculations. There is a calculation method how to calculate it. You calculate the capacity in outside of drill pipe and the inside of the drill pipe, and you are balancing both of them, spacers and the slurries. Here I have put one more option for under displacing for a few barrels. Why we are using under displacement? It reduces the contamination, because once you balance while drill pipe immersed, you are balancing spacer and slurry, but then you are pulling out of this drill pipe, and when you are pull out of this drill pipe, this cement slurry is just filling the volume captured by your drill pipe volume, right? Drill pipe itself, drill pipe body, let's call it. So when drill pipe body is pulling out of slurry, this volume is filled with the slurry inside from drill pipe, and you are getting this balance again. In order to reduce contamination while you are pull out of wall, we keep some more slurry inside drill pipe, and that's why it will cover the upper section of that plug. So this is the balance plug method. You see how it is balanced, spacer here and the slurry here while the drill pipe inside. Then they are pull out of the drill pipe. When you pull out of the drill pipe, this section is filled by slurry here, and you got the spacer outside. So this is called the balancing method for the plug. I would say that the 90% of the time, 94% of time, we are using balance plug. Not only us, I mean, everywhere balance plug is used. In one of the next sections, maybe we can cover a calculation for this one. It is easy. Let's say we need to balance, we need to spot 300 meter of plug. This is a little bit long. Let's call it 200 meter of plug. And to place 200 meter of plug, you are calculating all the 200 meter volume without this casing. Let's say it will give you, depends on the casing size, it will give you, let's say, 80 barrel of slurry. Okay, I know that I need to spot 80 barrel. Then I'm calculating capacity of this drill pipe and capacity of this annulus. And then I'm dividing this 80 barrel to two sections. I'm using, let's say, 65 here, 15 here, or I'm using 64, 60, 60, 20. It depends on the drill pipe. It depends on the drill pipe capacity. Like, let's say if you are using 5.5 inch drill pipe, you will have a more slurry inside drill pipe. If you are using the 275 by 8 tailpipe, then you will have a little bit less volume inside this drill pipe. So this is the balance method for cement plug placement. And then I will go for last one. Last one, it is also used. For this one, the main problem is the casing accessorizes, and then we need to have a locator. It is two plug technique. It is the same of the, like for casing cementing, what we are using, right? We are using top plug and bottom plug. Here we use the darts because plug itself is bigger for drill pipe, and sometimes they call that darts also plug. You can hear it. First wiper dart and then second wiper dart, it's called. You are pumping slurry head, and you are pumping spacer ahead. Then you are dropping first wiper dart, and then you pump your slurry. When you see here there is a locator sub. So locator sub is a drill pipe accessorizer which is catching this dart. And this dart is placed over this locator, and then you have pumped your slurry already, and then your second wiper dart is coming, and what it will be, it will push the slurry down. Slurry will go down, and then your second plug will come and sit over this first plug. So in this method, it is a little bit different from balance plug because you are not immersing all drill pipe inside that pipe. You will have only, let's say, you will have only a few meters of this pipe to be in there. And why it is a favorable method? Also because you are getting less contamination. Here in balance plug option, you will not be able to use any dart or any mechanical separator between slurry, but also there is a method here, foam balls. Sorry, I haven't put any photos here, foam balls. So this one we are using. So a lot of manufacturers have different colors. So these are the foam balls. These are from special material that are used, and in balance plug usually we are using this one because it helps to slurry, spacer, and the mud to be separated, and when they are separated, we are getting less contamination, and less contaminations means that you get a better quality cement slurry in your plug. But in this one, you are using real separator, mechanical separator darts, which are very efficient for separating slurry, spacer, and the mud, and you don't get almost no contamination. So I guess I completed, and we have already covered calculation section. So from my side, it's all together. It is all what I had. Yeah, if you have any question, I'm waiting for this. Guys, anyone having any question?
Okay, so I guess no questions.
You are welcome.
Yeah, so thank you very much, Munavvar, for the time, and it was very interesting and informative session. And I also want to say, if you have any questions for participants, if you have any further questions, you can send it to any team member of SPE BHOS, and we will forward it to Munavvar Hanım.
Yes.
Yeah.
And also, I will try to prepare some quiz from these calculation ones and some questions from the last session about like questions like which techniques we have, what, in which case we are using which techniques, and I will pass these questions to Vagif and Rahima. Probably they will help me to prepare some quiz, or maybe they will tell me how usually they do, and I will do myself. Okay, so let's see that for the till the next section, how like last section, how last two sections, how effective they have been. We will see. Thank you, Mehdi. Thank you, everyone. I'm happy to be there. Sorry, this day I was a little bit kind of sleepy and kind of tired, but in the next section I will be more energetic. Thanks to the last job I had yesterday, it was very tough one. That's why. Okay, I guess they will guys will share in the end of course all these materials with you, and I will send also presentations. You can merge all of them in one PDF file, or I will be in one PDF file. Okay, I will provide it, and then you will you can use as a reference in your next I don't know, trainings and exams, etc. Yeah, thank you very much. See you in the next section. Bye bye. Thank you for joining, guys.
Okay, I'm closing the meeting now. Thank you everyone for joining.
Bye bye. Thank you, Vagi, for helping. Bye.